All right, so lesson 4 of Unit 5. We've been talking about evaluating integrals, which we have determined that finding or evaluating an integral is actually finding the area under a curve. But I want to show you, this particular lesson is going to focus on this idea of a definite integral. And we kind of looked at that and worked with that in the last lesson, lesson 3, when we were finding the area under a curve from like 1 to 2 or 0 to 10. So this lesson, Unit 5, Lesson 4, is all about definite integrals. And if you're following along with our notes, the first example says, find the area of the region bounded by the graph of f of x equals x to the third, the x-axis, and the vertical lines that are defined by x equals 0 and x equals 1. So it always helps if you can have an idea of what the function looks like or the graph of the function looks like. It kind of puts things in perspective. So if you recall what the graph of f of x equals x to the third looks like, the graph itself looks like this. Okay, so that would be f of x equals x to the third. We want to find the area of the region that is bound by this graph, the x-axis, which is this axis here, obviously, and the vertical lines, x equals 0, here's x equals 0, and x equals 1. So we'll say that that's 1. Okay, so, so what is the region that is bound by the curve, the x-axis, and the vertical lines? Well, it's this region right here. This is the region that we are wanting to find the area of. And so we want to find the area from 0 to 1. So let's think about this. If we were to approach this from a rectangular approximation method, let's say we wanted to divide this region into 12 subintervals. So if we did that, if we use a rectangular approximation method, that means we need to know the width. And so how do you find the width again? You take 1 and subtract 0. And if we want to divide this into 12 subintervals, then we would divide by 12, and that would mean that each of these partitions were 1/12 in length. So what would our endpoints be? Our endpoints, I'm abbreviating, would start with 0, because that's 0. We know we're going to end with 1. And if each of the rectangles have a width of 1/12, then our endpoints are going to be 0 or 0 over 12, 1/12, 2/12, 3/12, 4/12, and so on until we get to 12/12. If I'm just going to pick one. If I wanted to use the left RAM approximation to find the area, then my width is 1/12, and I would need to multiply 1/12 by the sum of f of 0 using the left endpoint. So f of 0 plus f of 1/12 plus f of 2/12. And I would do this until I get to f of 11/12. And again, we're using 11/12 because we're using a left approximation method. Now, one of the things that I've noticed, if you're following along in my notes that I've provided, you're going to see that I have used actually V of 0 and V of 1/12, and that is a mistake. These are not correct. They should all be F's because my function is defined as F. Okay, so what does that turn out to be? Well, I end up with a 1/12 times F of 0 is going to be 0. When I substitute 1/12 into F and cube it, I get 1 over 1,728 plus, if I substitute, or when I substitute 2/12 and cube it, I get 8 over 1,728. And of course, all my denominators are going to be 12 cubed. So I know all my denominators are going to be 1,728. So that's good. The next endpoint would be 3/12 cubed, and 3 cubed is 9, not 9, but 27. Plus, and if I were to continue that, I would do that until I get to 100, or not 100, but 11 to the third. And 11 to the third is 1,331. The denominator is still 1,728. Okay, so these are simply coming from evaluating the function at all of those endpoints except for 12/12 because I'm using the left RAM approximation. So to cut through all of the math on this, when I do all of that calculations, I end up with 0.2100 something. So don't throw off your 2 zeros because remember, we have to have 3 decimal places. So if you chop it off to 0.21, that's not going to be good. You have to put your zeros. So anyway, the area under the curve of x to the third bound by the x-axis and x equals 0 and x equals 1 is approximately 0.21 units, whatever the units would be. Okay, so now let's say, I want us to say that, let's say that this function actually represents a derivative. Because if you, well, let's say that x cubed is actually a derivative. Let's call it, if I had said that this was y equals x to the third, let's say that that represents a derivative, which would be dy over dx. Well, if we recall, dy over dx is a derivative, which is a fancy way to describe slope. So, just thought I'd throw that out there. And slope, we recall, is change in y over change in x. So that means that, this is just a little review, a little reminder, then that must mean that dy over dx is the same thing as the change in y over the change in x. And if the change in y over the change in x, which is dy over dx, equals x to the third, I want us to, that's just something I want us to remember and to think about. So what if, what if I were to take this expression right here, and what if I were to multiply both sides of this by dx? So that would be dy, the derivative of y, is equal to x to the third times dx. Well, I want us to think about that for a second. If we go back to this idea of slope being a change in y over the change in x's, our change in x's, remember what our change in x's was here. when we were using rectangles, if I wanted to find the slope of the tangent line here, I would be trying to find the change in y's over the change in x's. Well, the change in x's here is remaining constant. It's the same thing. So that's actually, if we think about finding the area of a rectangle, that's considered our width, because that is remaining constant. And if I think about x to the third, what would I do with x to the third? What was the purpose of x to the third when we were working with rectangles? Well, that represented the height. So I have a height piece and I have a width. Well, this would represent area. So if I find in order for me to find the area of this function, which represents this, I can find the antiderivative of both sides. And what is the antiderivative of the derivative of y? That would simply be y equals, what's the antiderivative of x to the third dx? Well, that would be x to the fourth over 4. And since my boundaries go from 0 to 1, I'm going to put a 0 here and a 1 there. And if I evaluate this, what this is saying is to take our antiderivative and evaluate it from 0 to 1. Well, how do we do that? Well, we evaluate this using what's called the evaluation theorem, which we'll get to a little bit later. I simply take my upper bound, which is 1. I want to evaluate this function at the upper bound, and then I want to subtract this function evaluated at the lower bound. So it's 1 over, why did I put 0 there? That's 1 over 4. 1 to the fourth over 4 minus 0 to the fourth over 4, which is going to be 1/4. And I want you to think about that as a decimal. So 1/4 turns out to be 0.25. Compare those two values right there. 0.2100 is awfully close to 0.25. Now, why are they different? Which one is more accurate? Well, if you think about what we've said from the very beginning about approximating area, the more rectangles we used, or the more rectangles that we use, the more accurate and precise the area will be. Well, we only used 12 rectangles. What if we had used 20 rectangles? What if we'd used 50 rectangles? What if we'd used an infinite number of rectangles? If the more rectangles that we used here, guess what this number is going to get very close to? And that's going to get very close to 0.25. And so the nice thing about integrals and definite integrals is that definite integrals or integrals will give us a way to evaluate a function and approximate the area, and it will be precise as opposed to a good approximation. Okay, so this is the idea behind a definite integral. What does this mean? Well, this means that we want to find the area on a definite integral from 0 to 1. Okay? Okay, so let's look at the next example. Let's go down here to the next example. And by the way, I think once again I have on my notes that I've provided, I've said that this is the height and this is the width, and that's not correct. This is correct. This right here is correct. Because remember, the width is what stays remains the same. And the height is what we use to find, the function is what we use to find the height. All right, so moving to another example. Our next example, we are given a function, f of x equals 4 minus x squared. We want to, and I'm just going to go ahead and kind of sketch the graph out as I read this. This says to find the area of the region bound by this graph, and by the way, this is a quadratic. It opens down and its vertex is at 4. So there's our quadratic. We want to find the area of the region bound by this function, the x-axis, and one vertical lines at 1 and 2. So let's say that these are our vertical lines. This is going to be the region that we are interested in finding the area of. Okay, so rather than going through this rectangular approximation method, the cool thing is all we have to do is set up an integral, evaluate the integral, and we'll have our area. So let's talk about what this is going to look like. So since we want the area, that means we can set up an equation, 4 minus x squared. This is going to be our height. We need a width, which is going to be represented by dx. Our width is dx. And to put it in perspective, though, let's just do this again. If this is to represent area, okay? So if this is to represent area, then this is going to represent dy over dx will equal 4 minus x squared, which represents the height, how we find the height. Now, so if we take our dy over dx, swing the dx over, then I have 4 minus x squared times dx. And if you recall, like I said, dx represents the width. So we have this function now that represents, so dy equals area. And if we find the antiderivative of area, we're going to find our value. So if I evaluate this from our lower boundary to our upper boundary of 2, then this is what I'm working with. I'm going to still write it this way, dy from 1 to 2. The area's formula is 4 minus x squared dx. Now, what is the antiderivative? Well, what's the antiderivative of dy? If that is the derivative of y, then the antiderivative is simply y. And the antiderivative of 4 is 4x. The antiderivative of x to the second is x cubed. So I have minus x cubed over 3. And I'm going to evaluate this function from 1 to 2. And so what we end up with is y equals 4x, pardon me. I'm going to evaluate this expression at 2. So that gives me 8 minus 8/3 minus 4 minus 1/3. And then when I do all my calculations, this right here turns out to be 16/3. This turns out to be 11/3. And that turns out to be 5/3, which approximately is 1.667. So in order for us to estimate the area under that curve, all we had to do was write our function and set our boundaries from 1 to 2, find the antiderivative of this, and then evaluate. And this is the way that we can approximate a curve, approximate area under a curve that is between certain boundaries. So what did we just use? I'm going to pull this away now for just a second. I'm going to pull this away. And I want to go to our second page of notes. And what we've just talked about and used is this idea of the fundamental theorem of calculus. And this is a huge theorem. It is not a theorem that you're going to have to prove like you did in geometry. But this is a theorem that you need to know because you use it often. It says if f is a continuous, or if f is continuous on an interval a to b, then the integral of f of x dx from a to b will equal, now I'm using capital F of b minus capital F of a because I need to indicate that the capital F is the antiderivative of f. Okay? So, and I don't even really want you focusing on that because that can be confusing. So what you need to understand is that if this is the function, when you find the antiderivative and you evaluate the antiderivative at the lower and upper bounds, then you're using the fundamental theorem of calculus. So let's think about this. What does this mean? Well, if this is the antiderivative, this is the derivative. So looking at this example, we have I want us to evaluate the integral of x squared plus x dx from 1 to 2. And what this is really saying is, hey, find the area under this curve between 1 and 2. Well, here's what we have to remember is that this expression represents the derivative, and this piece right here represents height, and dx represents width. Okay? So, to evaluate this, we're going to find the antiderivative, x to the third over 3, plus x squared over 2, and we're going to evaluate this from 1 to 2. So, substituting 2 for x, I get 2 cubed over 3 plus 2 squared over 2, and then I will subtract substituting the 1 as well. 1 cubed over 3 plus 1 squared over 2. Well, then in the cleanup process, this is 8 over 3, this is 4 over 2, this is 1/3, this is 1/2, and getting all the same denominators so that I can clean this all up. Common denominator between all of these would be a 6, so this would be 16 over 6 plus 12 over 6. This would be 2/6 plus 3/6. Do your magic, and we end up with 23 over 6. So the value of this integral is 23 over 6. Now, what does that really mean? Or to put this in perspective, what does this really mean? Or represent, rather? Well, let's just do this. I'm going to slide my calculator underneath here. Okay? And I'm going to type in my function x squared plus x. And I'm going to graph this. I want to look at the entire graph. Well, not the entire graph, but a graph on a normal standard window first. What this is saying is that we want our x values to be between 1 and 2. So I'm going to go into my window, And I'm going to change my window to be, my x's to go from 1 to 2. I'm going to leave everything else the same. So what is this wanting? This is asking for finding the area under this curve between 1 and 2. Now remember, I have chopped off, x equals 0 is over here. In fact, if I do this, let me go do this. I'm going to change this from 0 to 3. Actually, you know what I'll do? I'm going to do this. I'm going to do a, let me show it a different way. I'm going to go from x equals 0 to x equals 5. And I'm still going to do from negative 10 to 10. But I'm going to show you a little something else I can do. I can do, I believe, this. I'm going to graph this. I'll just leave it like this. And our x equals 1 is right here. And our x equals 2 is right here. So I'm going to try something real quick. Draw vertical 4 at, well, that's not what I wanted. I'm going to do second draw. I need a vertical line. I want one at 1. Enter. There's that. And I'm going to go to second quit. And I'm going to do second draw 2. That's not what I wanted. Second draw 4 at 2. And so here's the region that we're wanting to find the area of. So what we found mathematically is that the area would be 23 over 6. And so the area of this expression, or this region right here, is 23 over 6. If we had used rectangles and we had divided this into, if we could possibly divide that into an infinite number of rectangles, we would get a value that is close to 23 over 6, which is like 3 and almost 4, but 3 point something that's close to 4. So that's the beauty of integration, or evaluating an integral. Evaluating an integral means find the antiderivative and then evaluate it from the lower to upper bounds. And that's what we did here. And we get 23 over 6. Okay? Fundamental theorem of calculus is often called the evaluation theorem. And it's because you're finding the antiderivative and then you're evaluating the antiderivative. All right, so let's look at the next example. And I'm going to kind of set this up and let you finish it out so that we can kind of close out this video. But here I want us to evaluate this function from 1 to 9, which means find the antiderivative of this and then evaluate it from 1 to 9. Well, before I do that, I need to do some cleanup on this expression. I'm going to divide each of these 4 terms. Nope, that's 3 terms. This term, and this term by t squared. So dividing these two, I get 2. Dividing these two, I'm left with the square root of t. And then I have this negative 1 over t squared. I'm going to take the t squared, bring it to the numerator, and that's where this term comes from. So I've cleaned this expression up. I'm going to rewrite the square root of t as t to the 1/2. And now the antiderivative we get is 2t plus 2/3 t to the 3/2 plus t to the negative 1. And then I'll go through and I will substitute my 9. I will substitute my 1. I will do all the cleanup. And if I did my math correctly, I should end up with like 292 over 9, which is about 32.444. So the value of this integral is approximately 32.444. And what that represents is the area. If I were to draw this graph, if I were to draw this function, then the area of that under the curve of that function between 1 and 9 and the x-axis is going to be about 32.444 units. So that is the fundamental theorem of calculus, which is a very useful tool in the world of calculus. So I will leave you with that to practice. And if you have any questions, again, please don't hesitate to reach out, and we'll see you again.